The first airplane, which flew some 40 years ago, left succeeding generations with a challenge to improve and perfect, develop and invent, to build and rebuild. From that first structure of wood and cloth has sprung a large and important industry. The basic principles known by the Wright brothers have since been developed into a complex science, embracing many fields of knowledge. Constant research has brought answers to endless problems, and each answer has marked a step forward in the progress of aircraft development. To a modern world, these advances meant a broader realization of aviation's values. During the war years, men who design and build aircraft were devoting their entire energies to the nation's fight needs, for aviation played a major role in our total mobilization. From their drawing boards came aerial weapons which greatly changed the character of modern warfare. Under the pressure of war, which has always given impetus to rapid technical progress, phenomenal advances were made in the design, engineering, and performance of military aircraft, with each designed for specific tactical requirements. Taken together, these aerial weapons brought to our air forces the fast, hard-hitting, long-range fighters which helped to achieve for this nation and our allies air supremacy and final victory. Well known to aviation research engineers for some time has been the fact that further development along the lines of the original basic pattern would eventually reach an impasse, beyond which efforts to improve speed and altitude performance would lead to prohibitive inefficiencies. Forward-looking men have for years been seeking new power systems to overcome these impending limitations. Systems capable of delivering greater horsepower, which can be more fully absorbed, smaller, lighter in weight, simpler, with less wear and longer life. The feeling has been that the answer might be found in an entirely different principle for the powering of aircraft, perhaps an engine without the usual reciprocating parts. Recently, interest has centered on a system of propulsion which gets its driving force from a powerful jet of gases. It is called thermal jet propulsion. Power by means of a jet isn't a new idea. Hero used it in his Eolipile over 2,000 years ago. Steam from the lower vessel rising through a hollow support entered the freewheeling hollow sphere. Escaping through two jets diametrically opposed, the steam caused the sphere to revolve. In the 17th century, Sir Isaac Newton, the English astronomer, proposed to drive a cart using this principle. Steam generated in the boiler would issue through the rear jet, propelling the cart forward. A steam cock regulated the speed. It didn't actually work, but its principle has been standing by these many years. 3 centuries later, in the small English town of Lutterworth, a countryman of Newton succeeded in developing a modern application of this principle. British engineers had long sought to develop jet propulsion for the powering of aircraft. In 1937, after 4 years of research and experimentation, Group Captain Frank Whittle, a Royal Air Force pilot since 1928, demonstrated the first successful jet engine. The program was accelerated in a secret workshop of Power Jets Limited, and in May of 1941, successful flight tests were made with an improved design. Important military potentialities were indicated and full information was disclosed to the United States Army Air Forces. The prototype engine was shipped to the United States, where the Air Forces assigned quantity production of the engines to the General Electric Company, long experienced in turbine manufacture. The design and manufacture of an airplane to be powered by these engines was assigned to the Bell Aircraft Corporation, innovators in fighter aircraft. In a call from the office of General H.H. Arnold, Commanding General of the Army Air Forces, officials of the two companies were invited to a conference in Washington, where the new project was launched, 3 months before America's entry into the war was to redouble its urgency. Utmost secrecy was as vital as speed in the execution of this project, and at Bell it was revealed at first only to the engineers whose job it was to design the airplane. There was little precedent from which they could benefit, for this was a whole new concept for aircraft power, nor was there time for wind tunnel programs or other lengthy research. The design had to be completed as quickly as possible and still measure up to current military aircraft, not on a one airplane basis, but for quantity production. During 2 weeks of intensive work, a number of designs for a twin-engine, single-place fighter were considered. Toward the end of that period, the best features contained in the many sketches were carefully analyzed, and a decision was reached as to the design to be submitted. For a final study in the short time allowed, a small model was made. This design, developed through the joint efforts of Army and Bell engineers, was approved and designated the XP-59A. The design underwent rapid development, and as the details were refined, the work of construction was begun. Loft templates were laid out as patterns for the parts. Holding fixtures were designed and erected for the construction of sub-assemblies. Forms were cast for the shaping of parts. For secrecy, the entire operation was set up as an independent manufacturing unit and staffed with a select group of craftsmen. Completed parts found their places in various sub-assemblies planned in accordance with quantity production requirements. The airplane began to take shape as these assemblies were brought together. Work that ordinarily would take months, perhaps years, was compressed into a fraction of that time by a day and night schedule. At General Electric, a huge new chimney had sprung up almost overnight. It was part of a vault-like test chamber rushed to completion for testing the British prototype and subsequent engines. To the men assigned to this work, the test cell seemed strong enough to protect the nation's gold reserve. Here, the engine was studied for adaptation to American production methods. The work of building the first engines was not centered in a secret plant as at Bell. The problem of security was solved in a different way. The parts for the jet engine were very similar to those of the airplane superchargers in production at the plant. The work was distributed to shops throughout the various factories, and the nature of the project further obscured by the designation Type I supercharger. In this way, the existence of the engines was known only to those few selected to assemble them. Within 6 months, the first American-built engine had been tested at General Electric. And as at Bell, the mechanism for continued production had been set up. Meanwhile, across the continent, the Army Air Forces had prepared a secret desert base for an intensive flight test program. The airplane arrived complete with engines which had been constantly rotated to protect the bearing surfaces from vibration in transit. It had been accompanied on its cross-country trip by a corps of mechanics and by a guard of military police to ensure its secrecy. The assembly of the airplane culminated months of searching and concentrated effort. For in its development, designers and engineers had been confronted by many problems and questions for which there had been no precedent. Only now, by operational tests of the airplane itself, could these questions be answered. One question was the intense heat from the jets. How would it affect the structure? A test was devised using chemically treated paints that would char at different temperatures, and the engines were started up in the ship for the first time. Each engine was given 3 5-minute runs. Result, heat effects were negligible. What about the jet blast? Was it dangerous for ground personnel? At moderate distances, it was found that heat was not excessive. No more precaution was needed than for the propeller slipstream of a conventional airplane, which might impair control of the airplane. This problem had been anticipated in the upswept tail design, but the exact characteristics of the jet stream could not be determined until performance data was available. A series of accelerated taxi tests extending well into the evening of the first day of testing provided the answer. Control was satisfactory. The next day, preparations were begun for the first actual flight. Robert M. Stanley, Bell's chief engineer, then chief test pilot, who had supervised the test program, was at the controls. As the airplane set out for its first test flight, it carried with it the hopes and confidence of the men who built it. But would it achieve the great promise they had foreseen in this new type of power? The success of this flight would have an important bearing on further progress in jet propulsion. The first test hop was 25 feet off the ground. Everything in order. With the control response good and the handling qualities proven, the airplane was ready for higher altitudes. It was taken to 6,000 feet, then 10,000, and then on up. The date was October 1st, 1942, a day which marked an important achievement in American aviation progress. In the short space of 1 year and 3 weeks, the complex problems involved in the design and construction of this revolutionary new airplane had been surmounted. In its first flights, it had achieved performance comparable with that of existing fighter aircraft. But of far greater importance was the impetus it was to give to future development. With jet propulsion proven first in Great Britain and now in the United States, its development on both sides of the Atlantic continued with all possible speed. Data on characteristics and performance of the engine were the first considerations, and features of the airframe were studied for further improvements and refinements. Production continued at General Electric and Bell, and soon other airplanes were added to the first. There were no allowances in this intensive program for delays. When rains made the base unsuitable for flying, the airplane was camouflaged with a dummy propeller to maintain secrecy, and the project transported to a nearby field where the collection of vital performance data could be continued. As additional airplanes were completed, they were designated for varied test purposes. One was shipped to the Royal Air Force in England, and by such constant interchange was the development of jet propulsion furthered by both nations. 2 more P-59s were earmarked for full-scale wind tunnel tests at the NACA laboratories at Cleveland and Langley Field. Here, the engines underwent high-speed test runs, and the airplane's aerodynamic characteristics were carefully studied. The data collected here in 6 months of testing were added to the growing fund of knowledge, which was to provide a basis for the expanding jet propulsion program in this country. 2 P-59s were also assigned to the Bureau of Aeronautics of the United States Navy so that the features of this new aircraft could be studied and evaluated for their purposes. Keenly interested in the possibilities of jet propulsion as a means for powering naval fighter aircraft, officials witnessed at a Navy experimental flight test base a demonstration of the performance characteristics of this type of power and its adaptability for the special requirements of carrier-based aircraft. Included in the demonstration were high-speed test runs, so that data could be assembled on the performance of jet propulsion as compared with other types of power for fighter airplanes. In this first airplane in the United States to be powered solely by jet propulsion, there was great interest as to the details of its operation. Here, as everywhere, pilots wanted to know how the new airplane got its power. The explanation usually boiled down to something like this. Remember back in high school when you studied elementary physics? Remember Newton's third law of motion? To every action, there is always an equal and opposite reaction. How it applies can be illustrated with a toy balloon. The energy which is used to blow up the balloon is stored inside it in the form of pressure. This pressure acts with equal force all around the balloon as long as it remains closed. When the neck is opened, however, the forces acting on that end cause the air to rush out through the opening. The opposing forces are no longer balanced and they react, propelling the balloon in the opposite direction. This propulsive force is created by 2 elements, pressure and velocity. In thermal jet propulsion, the energy which in the balloon was supplied by the boy is here created by combustion of fuel and oxygen, producing the necessary pressure and velocity. The parts of a jet engine are a cold air inlet and diffuser, a mechanical compressor which compresses the air, a series of burners where the oxygen of the air is combined with fuel and is ignited. There is a ring of these burners around the entire circumference of the engine. A turbine which takes some of the power out of the escaping gases to drive the compressor by means of a shaft. And a tailpipe which conveys the gases to the jet nozzle. Air traveling at a velocity equal to the speed of the airplane approaches the inlet. Inside, it loses some of its speed but picks up in pressure. Drawn into the compressor, the air is highly compressed. In the burners, this air is sprayed with fuel and ignited. The intense heat generated causes the gases thus formed to expand rapidly with great force, and they rush to escape, gaining terrific velocity. Part of the power of the escaping gases is used to rotate the turbine, which in turn drives the compressor. The remaining power further increases the velocity of the gases so they blast out through the jet nozzle. This, then, is the action of the heat, pressure, and velocity. The reaction is the movement of the airplane forward. This method of aircraft propulsion presents many advantages. With no reciprocating engine movement, the airplane is remarkably free from vibration. Propeller torque is completely lacking, and in the P-59, with its two jets so close to the center line, single engine performance presents no problems. Highly significant in surmounting present aircraft limitations is the fact that at the extreme altitudes and speeds where propeller-driven airplanes begin to drop off in efficiency, jet propulsion characteristically becomes more and more efficient. The jet engine is lighter and simpler than conventional engines, with only 10% the number of moving parts. The absence of propellers makes possible a shorter and lighter landing gear. This, together with a low center of gravity, due to engine placement, makes for safer landings and better ground handling characteristics. This airplane incorporates a pressurized cabin for maximum pilot efficiency at high altitudes. In the cabin are the usual stick and rudder pedals for the control of the airplane, but noticeably absent are various instruments needed with conventional engines. Simple push buttons start the engines, which are regulated by means of standard throttles. These many advantages of jet propulsion promised important possibilities for aviation's future, but of immediate value were its military applications for a nation at war. On January 26, 1944, the Army's Chief of Staff, General George C. Marshall, General H.H. Arnold, Commanding General of the Army Air Forces, the Commander-in-Chief of the Navy, Admiral Ernest A. King, Major General B.W. Chidlaw, and Lord Halifax, the British Ambassador, together with a select group of those most vitally concerned with the immediate development of jet propulsion, assembled at Bowling Field to witness a demonstration of the P-59A. A survey was presented by General Chidlaw of the advances achieved in this first American jet-propelled airplane. He related the progression of events in its design, building, and subsequent testing, and summarized the results of the experimentation which it made possible. After being briefed on the airplane's principal features, those present saw a demonstration of its flight characteristics. After the demonstration, the airplane was made available for closer scrutiny so that they could learn at first hand more about the adaptability of this type of airplane for military use. To the leaders of our armed forces, this innovation presented a concept in air power which could have an important effect upon the airplane's role in future war strategy. To realize this expected military value as quickly as possible, more engines and more airplanes were needed for continued expansion of the jet propulsion program. At General Electric, production requirements had become so extensive that a new plant was especially constructed for this program. In contrast to that first improvised engine test cell, there was now a battery of well-equipped test bays where the newly completed engines were run up for the first time and given complete operational checks. In spite of this expansion, secrecy precautions were still rigidly adhered to. At Bell, the production technique which had speeded the manufacture of its other fighter planes was adopted for the new airplane. The entire operation had been moved from the secret shop where the prototype had been built to a restricted area in the main factory. Here, additional airplanes were rushed to completion for the many important purposes they could serve. With these aircraft, the Air Forces was equipping the first group for training pilots in the fighting tactics of jet-propelled aircraft. Well suited to this program were the P-59s, with their safety record of thousands of hours flown during the testing program without pilot injury. Of even greater value was the P-59's importance in the advancement of jet propulsion itself. With its twin engines, it was ideally suited to the extensive testing being conducted in the nation's program, which began with the development of this airplane. Initiated by the Army Air Forces, this project was supervised by Brigadier General Frank Carroll, Chief Engineering Division, Air Technical Service Command. He and many others, Air Force officers, engineers, and pilots, working constantly together, were largely responsible for this first American jet propulsion airplane. The P-59 AIRACOMET had achieved in a short span of months performance comparable to that of advanced conventional airplanes developed over a period of many years. But its accomplishments are secondary to the broader achievements which it portends. In its production, the Bell Aircraft Corporation has pioneered in a new type aircraft which is certain to be closely allied with the expanding frontiers of aviation. Both in Great Britain and in the United States, the work of further development has been greatly accelerated. The story of jet propulsion is the story of progress, and in this first chapter, the P-59 is but an introduction. Still largely unexplored, the potentialities of this new concept for aircraft power seem endless. Its promise for the future of aviation almost unlimited.